In this video we're going to look at shapes of simple molecules or polyatomic ions, just fairly straightforward ones. To start with, we're going to look at a theory known as the valence shell electron pair repulsion theory. Well, that sounds like a mouthful. It basically means that pairs of electrons repel each other, and if you look at a central atom in a molecule, then all we need to do is count the number and the type of electron pair around that atom. If I look at an electron pair, you can have a bonding pair of electrons, which is just a covalent bond, and you can have a lone pair of electrons. And we're going to look at that in a bit more detail now. So this theory basically means that pairs of electrons repel each other, but not all pairs of electrons are the same. For example, you can have a lone pair of electrons, such as the one I've drawn here. I've just drawn an arbitrary atom X, and I've put a lone pair of electrons on top of each other. That's a non-bonding pair of electrons. Now, that sits in an orbital very, very close to that central atom. That basically means it takes up a lot of space around the atom. If it takes up a lot of space, it's probably going to have a better repelling power than another type of electron pair, such as the bonding pair. If we've got a bonding pair of electrons, what happens is that instead of just going into our standard atomic orbitals, which we looked at in the previous section, we now see these as things called molecular orbitals. Don't get too bogged down by that. Effectively what that means is your pair of electrons occupy, let's say, an electron cloud in between the two atoms, but because you've got two atoms here, this one and this one, that electron cloud just gets stretched out. So if I consider X to be a central atom, then if that electron cloud is stretched out, that's not going to take up as much space around the central atom as my bonding pair there. So this basically means that lone pairs repel more than bonding pairs of electrons. Now when we're looking at the shape of a molecule, we only look at the actual bonds between the atoms themselves. So while lone pairs have a really, really massive impact on the shape, we actually don't see them. We'll see the bond between two different atoms. So now what we're going to do is we're going to look at electron pairs around a central atom and see what shape we have, starting from 1. So I've got one bonding pair of electron. Here I can look at HCl. Well, that's going to be a linear shape. So in red there I've written the shape. That's going to be a linear shape. Then if I increase the number of electrons around a central atom and now call that central atom beryllium, what I'll see is that the beryllium here, beryllium dichloride, this is, has two chlorine atoms. It's only got two electrons around its outer shell. They're bonding electrons. They go as far away from each other as possible, and that means the shape is linear. What happens if I increase that to 3? Well, let's have a look. If I increase that to 3 bonding pairs, I get a system like this. So boron trichloride, for example. You've got no lone pair of electrons, you've just got 3 bonding pairs which repel each other equally and get as far away from each other as possible. We get a shape called trigonal planar, and the angle between those bonds is 120 degrees. So that's boron trichloride. 3 bonding pairs, trigonal planar shape. So next we're going to look at what happens when we get 4 bonding pairs of electrons. Well, 4 bonding pairs of electrons, we get a situation like this. So we've got a carbon surrounded by 4 hydrogens. They're all bonding pairs of electrons. They repel each other equally, so they get as far away from each other as possible. Now, to explain what this dashed line here means and this wedged here line there means, we need to have a look at 3 dimensions. Basically, if I think of this, that orange line there is the line of the page. That dashed line there means it's going behind the page, and this wedge here means it's going in front of the pane. So I've brought a ball and stick diagram here of methane. So what you can see is if this was a plane of the page like that, that hydrogen is going away, and this hydrogen is going out towards you. You can buy molecular model sets online. They're really, really handy. They'll be able to help identify the shapes of the molecules. That's known as tetrahedral anyway, and it's got 4 bonding pairs of electrons. Now we're going to look at a system where we have 4 pairs of electrons, but they're not all bonding pairs. So let's have a look at this one here. We've got ammonia, Nh3. We know that nitrogen has 5 electrons around it. We know that 3 of those are covalent bonds from the covalent bonding video we looked at earlier, and you've got a lone pair of electrons sitting on top. So looking at the central atom, we've got 3 bonding pairs and 1 lone pair. Well, we know that lone pairs will sit on top and will repel more than bonding pairs. So what happens here is they push the hydrogen atoms down. Okay, and here's a ball and stick model of it. Okay, if the lone pair is sitting on top like that, it pushes those hydrogen atoms down. So what you end up with is something called a pyramidal shape. So that's with 3 bonding pairs of electrons and 1 lone pair of electrons. Next, we'll stick with 4 pairs of electrons, but we're going to go with 2 bonding pairs of electrons and 2 lone pairs of electrons. So looking at water now, water has a V shape. It's got 2 bonding pairs and 2 lone pairs. The lone pairs just sit on top. If you look at the ball and stick model like this, they sit in a kind of a perpendicular arrangement between the bonds there like that, the oxygen-hydrogen bonds. And they push those oxygen-hydrogen bonds down away from being linear towards being V-shaped. The bond angle between the 2 covalent bonds is 104.5 degrees. So that's pretty much it for the simple molecular substances for the Leaving Cert course. If I increase the number of electron pairs around the central atom to 5, I get what's known as a Trigonal Bi-Pyramidal, like this. And if I increase the electron pairs around the central atom to 6, I get an octahedral shape. Okay, you don't need that specifically for this section of the course. It's called octahedral because, well, if I just look at it like this, it's got 1, 2, 3 and then 4 behind it, faces on the front, and it's got 4 faces on the bottom, so it's octahedral, 8 faces. In the same way that tetrahedral means 4 faces. These are really prevalent in transition metal compounds, but we're not going to look at them now. They might crop up in the course later on. So that's it with shapes of molecules. We know that shape is dictated by electron pairs around a central atom. Electron pairs repel, lone pairs repel more than bonded pairs. Count the number of electron pairs, i.e. the bonding pairs and lone pairs, and you should be able to work out the shape from the shapes that we've done here.